Hello everyone, welcome to this video of complex number. Today we are discussing about complex number and exploring its geometric meaning. A complex number is an extended version of real number in the form of x plus iy, where x and y both are a real number. Euler introduced the imaginary unit I, which is read as iota, for the square root of minus 1, with the property I square plus 1 equals to 0, means I square equals to minus 1. Therefore, imaginary unit I is the solution of an equation x square plus 1 equals to 0. In the complex number, horizontal axis represents the real part and the vertical axis represents the imaginary part. The plane where a complex number lies is called complex plane or argand plane. Here, 1 is the unit for real part and I is the unit for imaginary part. A complex number in the plane can be seen as a point. For example, a complex number like 2 plus 3i is located 2 units to the right and 3 units to the up from the origin. So let us start a discussion about I. So what is I? What exactly it is? Please note that I is not a non-existent number, nor it is confined to the concept of imagination only. But what does I represents geometrically? On your screen, you can see that it is like taking an anti-clockwise quarter turn in the complex plane. So please note that I is not just a number. It is a quarter turn in the anti-clockwise direction. Therefore, when we are asked to prove I square equals to minus 1, we can write I square equals to I into I, where one I works as operator and the second I we will put the number like 0, 1. And then as an operator, it will give anti-clockwise quarter turn. That is why 0, 1 changes to minus 1, 0, and which is minus 1 times 1, 0. Therefore, it is minus 1 times 1 because 1 is the unit of real axis. Therefore, it is minus 1. Dear friends, what is the absolute value of a complex number? If you have a complex number z equals to x plus iy, the absolute value denoted as z modulus is a non-negative real number defined by a formula z modulus equals to the square root of sum of the squares of x and y. Geometrically, the absolute value of z represents the distance from the complex number z from the origin. Please note that in the complex number, the order property is meaningless. Means comparing two complex numbers, say z1 and z2, and using the trichotomy relation means less than, greater than or equal to is actually meaningless unless both numbers are real. Why is this case? Well, the complex plane adds a dimension, both real and imaginary, to the complex number system. Without a clear sense of direction in this two-dimensional space, saying one complex number is less than or say greater than doesn't have a well-defined meaning. This is why the order property does not hold in the system of complex number unless both are reals. Next, we will talk about the conjugate. If we have a complex number z equals to x plus iy, then its conjugate denoted by z bar is defined as x minus iy. On your screen you can see the formula for the conjugate of a complex number z, which is equals to x minus iy. Geometrically, take a look at the visual representation on your screen. If z is represented in the complex plane, then z bar, which is a conjugate of z, is obtained by reflecting z across the real axis. The conjugate of a complex number z is not just a mathematical operation. It is a geometric reflection on the real axis. A beautiful connection between algebra and geometry. Thank you. In this video, we are going to discuss about polar form of complex number. Instead of representing a complex number as x plus iy in rectangular coordinates, the polar form expressed the complex number in terms of its magnitude r and amplitude means the angle theta. On the screen you can see the polar form definition of a complex number, which is r times the quantity cosine theta plus I times sine theta. The polar form of complex number is very useful to simplify complex number operations like multiplication and division, making calculation very straightforward. Using the concept of right angle triangle and trigonometric ratio, it is very straightforward to calculate the value of z, which is x plus iy, in which x is r cos theta and y is r sin theta, provided that the absolute value of the complex number z modulus is equal to r. Among the several benefits, one is the multiplication, which we are going to see. Let z1 r1 cos theta 1 plus I sin theta 1 and z2 r2 cos theta 2 plus I sin theta 2 are two complex number. Then their multiplication is r1 times r2 times cos theta 1 plus theta 2 plus I sin theta 1 plus theta 2. For the straightforward proof, we will multiply algebraically. Once we multiply the term, in place of I square, we will write minus 1. And then we will organize the term without coefficient I and with coefficient I, in which cos theta 1 plus theta 2 represents the first part and sin theta 1 plus theta 2 represents the second part. With this, we conclude that the multiplication of a two complex number is the product of its magnitude and the sum of its amplitude. The essence of polar form of a complex number can be seen in a theorem called argument of the product of two complex numbers z1 z2 is the sum of the argument of z1 and z2. Means when we multiply two complex numbers z1 and z2, we will get r1 times r2 the quantity as a magnitude and theta 1 plus theta 2 the quantity as amplitude. Similarly, the polar form can also be used to find the inverse of a complex number. Means z r cos theta plus I sin theta be a complex number, then its inverse will be 1 by r times cos theta minus I sin theta. For the proof part, let us suppose the inverse of a complex number z, which is z inverse, is capital R times cos phi plus I sin phi. Then by the algebra of complex number, z into z inverse is 1 in the extended form, which is r cos theta plus I sin theta times capital R cos theta plus I sin theta equals to 1 0. By the ordinary multiplication of complex number, we will get that the result is R times R cos theta plus phi plus I sin theta plus phi is equal to 1 0. Equating the real and imaginary parts separately, we will get R times R cos theta plus phi equals to 1 and R times R sin theta plus phi equals to 0, which gives that the capital R equals to 1 by R and phi equals to minus theta. Thus, the complex number Z inverse is 1 by R times cos theta minus I sin theta. Next, we will talk about Euler's formula. In complex number, Euler's formula established a fundamental relation between trigonometric function and complex exponential function. The Euler form of a complex number is given by z equal to r times ei theta, where r is the magnitude of complex number z, e is the base of the natural logarithm, I is the imaginary unit, and theta is the argument of the complex number z. This exponential function is sometimes denoted by cis x, cosine plus I sin x. Basically, the strength of Euler form is e to the power I theta equals to cos theta plus I sin theta. Based on it, the Euler form of complex number is derived. Now we will prove it. Consider a function f theta given by f theta equals to cos theta plus I sin theta divided by e to the power I theta. It can also be written as f theta equals to e to the power minus I theta times cos theta plus I sin theta. Differentiating gives by the product rule, we get f prime theta equals to 0. Once you do the differentiation, the right side becomes 0. Thus, we find that f theta is constant. Since f0 equal to 1, it concludes that f theta is also equal to 1 for all theta because f theta is constant because its derivative is 0. For this reason, we can write that f theta means 1. Therefore, 1 equals to e to the power I theta times cos theta plus I sin theta, which concludes that e to the power I theta equals to cos theta plus I sin theta. Therefore, we have a complex number z equal to r ei theta. This form of complex number can also be derived using the power series. Using the power series expansion, we get e to the power I theta equals to 1 plus I theta minus theta square by 2 factorial minus I times theta cube by 3 factorial plus theta to the power 4 by 4 factorial and so on. So the expansion can be organized collecting the terms without coefficient I and with coefficient I. Since the expansion of cos x is equal to 1 minus x square by 2 factorial plus x4 by 4 factorial and so on, and that of sin x equal to x minus x cube by 3 factorial plus x pi by 5 factorial so on. If we replace the x by theta, then we will get the first categorization as cos theta and the second categorization as sin theta. For that reason, e to the power minus I theta equals to cos theta plus I sin theta. Now we will talk about de Moivre's theorem. We have learned that we can convert complex number to a polar form. Now we are going to work with the formula developed by French mathematician Abraham de Moivre, which is very instrumental working with products, quotients, powers and roots of complex number in much simple form. On your screen you can see that the statement of de Moivre's theorem, which states that for any complex number z in the polar form r cos theta plus I sin theta, raising it to the power of n is equal to r to the power n times the quantity cos n theta plus I sin n theta. It allows us to understand the rotation and scaling effect when raising a complex number to a power n, where n is a natural number. For the proof, we will follow the mathematical induction method. Let's start with the case 1, where n equals to 1. Then the given complex number z can be written in the form z to the power 1 equals to r to the power 1 cos 1 times theta plus I sin 1 times theta, which ensures that z to the power n equals to r to the power n cos n theta plus I sin n theta when n equal to 1. Now we start by case 2, in which z to the power 2 equals to r to the power 2 cos 2 theta plus I sin 2 theta. This we have already proved in the polar form. So when n is equal to 2, the theorem holds. Now we start the case 3, the hypothesis step, in which we suppose that this theorem is true for n is equal to k. Means z to the power k equals to r to the power k cos k theta plus I sin k theta. Now we will prove the inductive step. This is case 4 and we assume that n is equal to k plus 1. Then z to the power k plus 1 equals to z to the power k times z. Since z to the power k is already proved in the hypothesis step, we multiply it by ordinary multiplication. We will get that r to the power k plus 1 times the quantity cos k theta plus theta plus I sin the quantity k theta plus theta. Taking theta as a common in the quantity of arguments, we conclude that z to the power n is equal to r to the power n cos n theta plus I sin n theta when n is equal to k plus 1. Therefore, for any n, the z to the power n equals to r to the power n cos n theta plus I sin n theta is valid. We conclude the proof of de Moivre's theorem. There are many advantages of de Moivre's theorem. Among them, we will see that how it helps to multiply. Here 1 plus I is a complex number which has magnitude root 2 and argument pi by 4. Means the distance from the origin to the complex number is root 2 and the angle made by the complex number with x-axis is pi by 4. Taking r equal to root 2 and theta equal to pi by 4, we can multiply the complex number 1 plus I to the power 6. We can find the result of complex number 1 plus I to the power 6 using de Moivre's theorem, which tells that the answer is root 2 to the power 6 times cos pi by 4 times 6 plus I sin pi by 4 times 6. With a basic calculation, we get the result minus 8i. In this video, we are going to discuss about nth root of a complex number. At the end of watching this video and doing the assigned activities, as a learner, you will be able to understand the concept of nth root of a complex number, apply knowledge to calculate nth root of a given complex number, demonstrate the ability to express nth root in both polar and rectangular forms, and draw a diagram of nth roots of a given complex number. As a prior knowledge, you need to understand the de Moivre's theorem, which tells that if z is a complex number in the polar form, then the nth power of z is equals to r to the power n times cos n theta plus I sin n theta. For the instructional process, we use interactive simulation to visually represent the nth root of a complex number. Please try it for better understanding. On your screen, you can see the link of this simulation. Please click in this link and try to understand the concept. What does the nth root of a complex number represents for? Please note that the nth root of a complex number are evenly distributed in a circle by angles 2 pi by n. Any non-zero complex number can have exactly n distinct roots. The roots lies in a circle of radius, the absolute value of z to the power 1 by n, which centered at the origin and is spaced out evenly by angles 2 pi by n. Each of these roots are Let's say Rk equals to nth root of R times cos theta plus 2 pi k by n plus I sin theta plus 2 pi k by n, where k runs from 0 to n minus 1. Each value of this k gives the root of the complex number. By using de Moivre's theorem, we will be able to derive this formula of nth root of complex number. Let nth root of the complex number z is w, which is capital R times cos phi plus I sin phi, such that the nth root of z equals to w. That is why w to the power n equals to z. Now we will substitute the value of w and z. Applying de Moivre's theorem, we will get this expression. As we know that let z be a complex number, then by de Moivre's theorem, the z to the power n equals to r to the power n cos n theta plus I sin n theta, which we have applied here. Now, equating the real and imaginary parts separately, we get r to the power n equals to r, cos n phi equals to cos theta, and sin n phi equals to sin theta. By ordinary simplification, we get r equals to nth root of small r and n phi equals to theta plus 2 pi k, because sin and cos both are periodic function whose periods is 2 pi, and to get the valid values for both cos and sine, it comes in the period of 2 pi. That is why the n phi equals to theta plus 2 pi k. With a bit of more calculation, we will get phi equals to theta plus 2 pi k by n. Thus, the nth root of complex number z is w equals to r cos phi plus I sin phi, which is w equals to nth root of r times cos theta plus 2 k pi by n plus I sin theta plus 2 k pi by n for k runs from 0 to n minus 1. Here we have simply substituted the value of capital R and phi from above calculations. So this is what we call the nth root of a complex number z. Now we will see one example. In this example, we will find the square root of I, where I is a complex number. So to solve this problem, we will use the formula for the nth root of a complex number z. Since I is a complex number, the magnitude is 1 and the amplitude means the argument is pi by 2. Therefore, the extended form of complex number I is cos pi by 2 plus I sin pi by 2. With this, we will be able to find the square root of I, means two different roots of a complex number I. That is why the roots will take when the value of k is 0 and k is 1, because the value of n is 2 in this case. Taking the value of k equal to 0 in the formula, we will get that cos theta plus 2 pi k by 2 plus I sin theta plus 2 pi k by 2. Here the value 2 is replaced in the place of n in the formula. Now we will put the value of k equals to 0 and we get the answer cos theta by 2 plus I sin theta by 2. Then the solution is cos pi by 4 plus I sin pi by 4, and which is in the rectangular form 1 by root over 2 plus I 1 by root over 2, where the first root is labeled by R1. Now we will find the second root R2. For this, we will take the value k equals to 1. Putting the value k equals to 1, we will get that the answer is cos theta plus 2 pi by 2 plus I sin theta plus 2 pi by 2. With this, the solution is cos 5 pi by 4 plus I sin 5 pi by 4. And in the rectangular form, the answer is 1 by root over 2 minus I 1 by root over 2. On the screen, you can see the square root of I, which are labeled. Now, for your better understanding, here is a problem which is based on real life situation, and it is suggested to you to solve it. Impedance, which is a concept used in the field of electrical engineering and physics to describe the flow of alternating current, AC. Impedance is the combination of resistance and reactance, and it is represented by a symbol Z. It is expressed in terms of ohms. In a circuit with both resistive and reactive elements, impedance is a complex quantity typically denoted by Z equal to R plus Ix, where I is the imaginary unit. Here is a question. In electrical engineering, a circuit has an impedance represented by the complex number Z equal to 8 plus 6I. The engineer need to design a component with an impedance that, when cubed, matches the original impedance. Now solve the following questions. Calculate the magnitude of Z and amplitude theta. Determine the cube root of the original impedance in a polar form. Design a new component with the impedance Zn such that cube of Zn matches the original impedance. And express the new impedance in a rectangular form and calculate its magnitude and angle. With this, thank you very much for this video. Please feel free to write if you need any further information.